Good afternoon, everybody. My name is Sunny Delara. I'm a senior applications engineer in the DragonFly team. I'm going to switch the screen here real quick. So what we're doing for this live demo is we're going to demonstrate high IOPS, high bandwidth, low latency out of a single NVRAM card attached into an Intel equipped server. We have a single socket CPU server with a processor running at 3.6 gigahertz, 8 cores with 8 gig of RAM. The first test we're going to run is the 4-byte. Here we go. Is the 4-byte test where we were able to achieve up to 9.9 million IOPS with a latency of about 100 nanosecond. I'll run that a few times here.
So at this point, the NVRAM just maps into the main system memory space, and we're just treating it like memory. So,
and what is key to know in this thing is that we can randomly access any part of this NVRAM.
right. Well, it's just memory.
It's memory. It's not like a small NVRAM in front of a large flash array or something like that. In which case, the only way you can achieve this kind of performance is if you're doing sequential writes. But if you're doing it randomly, then you can't do it with a small NVRAM in front of a larger flash array.
Okay. So, couldn't I achieve basically the same thing with one of Viking's NVRAM DIMMs?
It's possible. The problem with NVDIMMs, actually I have a slide on that, is that NVDIMMs have not are not yet in a state where they can be widely used. There are many reasons for that. One is they require some modifications to motherboards. Some support is required. Some BIOS support is required. You have to make modifications to the kernels and drivers.
and since you've got a PCI interface, all that goes away.
Yeah, that goes away. And the other problem is many NVDIMMs that we've looked at, they actually run at a slower clock. So if you stick it in the system, all the other DIMMs in the system also have to run slower, which is sort of the bigger knock.
Right.
So you haven't seen too many systems actually deploy those NVDIMMs yet.
And if I run out of capacitor, then it becomes volatile.
Yeah.
Where you guys can flush to flash.
Yeah.
Just wanted to add a plug. Based on our marketing guy, he said 9.9 million IOPS is as good as 10 million IOPS. Round it off.
Only a marketing guy would say that.
This next
I
test
see.
here is.
So is the motto on this product, this one goes to 11?
Theoretically, it can be.
You know, Spinal Tap logo on it.
Now you'd have to pay for that.
So this test is with 4K block size, 8 threads, 8 queue depths. As shown in the WS column here, it's where it shows 630K IOPS. This test runs for about a minute.
So do you present a block interface also, or do
Yes.
I, run a RAM disk program?
No. So the DMA access is through the block interface,
Okay.
and the byte access is through like a character device.
So the next test we're going to run is the 3.2 or the 16 kilobytes, 16K block size. We're able to achieve up to 3.2 Gbps bandwidth, as shown in the WMBps column. We're running it with 4 queue depths, 4 jobs or 4 threads in this particular profile. And then the last test would be a small block size of 512 bytes. So in smaller block sizes, we're able to achieve as high as 720K IOPS. So either 512 bytes, 1K, or 2K.
So one of the main observations here is that since it's DRAM, the performance stays consistent, never changes, right? As opposed to flash-based systems where it'll degrade over time.
And that's the last demo. I think the pause has something to do with our wireless connection. Yeah. So that concludes the live demo.
Thank you.